Welcome back. The objective of this video is to solve rational inequalities. When solving rational inequalities, it's important to locate both the zeros and the undefined values. So we're going to be working with both the numerator and the denominator. Remember that when f of x or y is greater than 0, that means the graph of x is above the x-axis, or our positive y's, and f of x is less than 0, we're looking for our negative y's, or our graph lies below the x-axis. Our process here is to isolate the inequality so that 0 is on the right-hand side. So we will move things over. We might have to find a common denominator and set it, well, not equal to 0, but put 0 on one side, usually the right side. Be sure the left side of the inequality is a single rational function. So here we might need to get a common denominator, so we just have one rational function. We'll factor the expressions of the numerator and the denominator and set each equal to 0. We've done that before, and we'll use those solutions to find values in our sign chart. So we're going to be drawing that number line and evaluating for positive and negative, as we have done in the past. So create a sign chart, mark the values where the denominator is 0, and those values will never be included in the solution. Where the denominator is 0, that's where our function does not exist. Test values in each interval, determine positive or negative, and interpret the sign chart based on our inequality. And then write our answer in interval notation. So in example 3, we're asked to solve the inequality r of x for greater than or equal to 0. So we're going to want to find the positive values, including 0. And we'll use the graph shown below. So we know from both the graph and from our rational function, we have an x value equal to 2. We have an x-intercept, and it appears we also have vertical asymptotes at 3 and negative 3, and that does also correspond to factoring our denominator and finding our restrictions that x can equal plus or minus 3. So we have critical values at negative 3, 2, and positive 3. And the positive 3 and negative 3, those will not be included in the solution because that's where our graph does not exist. And so now we'll just go ahead and do our testing process. Certainly we can look at our graph and see what's going on, but if we test a value like negative 5, we can see here that with negative 5, we end up with a negative in the numerator and a negative times a negative in the denominator, which gives us a negative over a positive. So overall that's negative, and that corresponds to what we have in our graph. Between negative 3 and 2, I might test 0. So these are my test values up here. And when I test 0, well, my numerator is negative, and my denominator, each factor, becomes a positive times a negative. So that's a negative divided by a negative. Overall, that's a positive, and that corresponds to what's on our graph. Between 2 and 3, I might test something like 5 halves or 2 1/2. And when I do that, I get a positive over a positive times a negative, and that is a negative value. And sure enough, that corresponds with what's on my graph. And then I might test something like 10, and I end up with a positive over a positive times a positive, which is a positive. So since I want positive values, I'm going to want the values between, so r of x is greater than or equal to 0 from negative 3 to 2 inclusive, and in union with 3 to infinity. Sample 4, we've got a polynomial function that's already factored. This isn't even a rational function, it's just a polynomial. And we want the factors to be less than or equal to 0. So we want negative values, and it's going to be inclusive. We have critical points at x equals 1, x equals 2, and x equals 4. So I'll plot 1, 2, and 4. And then we'll do our sign chart. So I might test something like 0, and when I put 0 in, I get a negative times a negative times a negative, which is going to be a negative value. So we like that one, that's going to be true. Between 1 and 2, I might test like something like 3 halves, and that's just going to be a positive times a negative times a negative, which is a positive times a positive, which is positive. We want negative values, so we don't want that region. We won't use those. Between 2 and 4, I might test something like 3. So we'll end up with a positive times a positive times a negative, which is going to be a negative value. So that one's true. We like that one. We're happy with that region between 2 and 4. And then from 4 to infinity, I might check like 10. And all those are positive. Positive times a positive times a positive is positive. So I don't care about the magnitude. I don't care what that multiplies out to, because we're evaluating above and below the x-axis. All we care about is whether it's positives or negatives. So the ones we like are from negative infinity to 1 and inclusive, in union with 2 to 4. So we don't like this last positive one because we wanted negatives, in union with 2 to 4 inclusive. So that guy out here we don't want. Example 5, we want to solve this rational inequality. We need to set one side equal to 0, so we have x plus 1 over x minus 3 minus 2 is less than or equal to 0. But we don't have one fraction, so we're going to need a common denominator. So let's go ahead and get our common denominator and simplify this into one fraction. So I multiply the 2 by x minus 3 over x minus 3, which is just 1. And then we'll simplify this and put this all over our common denominator of x minus 3. So I distribute my negative 2 through, and I get x plus 1 minus 2x plus 6 all over our common denominator of x minus 3. So I simplify my numerator to negative x plus 7 all over x minus 3, and I see that my critical points are at 7 and 3. So I can put those on my graph, and I can do my sign chart and evaluate. I'm going to evaluate 0, 5, and 10. And when I evaluate 0, I end up with a positive over a negative, which is negative. So I like that region. When I test 5, I get a positive over a positive, which is a positive. So that region I don't like. And then when I test 10, I get a negative over a positive, and that is a negative value, and so that one I like as well. Since 3 was one of our critical point, which made our function undefined, that's not going to be inclusive at 3, so we're happy with negative infinity all the way up to 3, but not including 3. But 7 just made the numerator 0, and we were happy with it equal to 0 because this was inclusive. This was a closed dot here or a bracket, so we'll go from 7 to infinity. In sample C, that one is also already factored for us. We have one rational function. We have zeros at 3 and negative 2. and we're going to be inclusive at those points. And we have an asymptote or an undefined at positive 2, so that's where our function's not going to exist, and we're going to be non-inclusive there. So I'll mark my critical points on my graph, -2, and that's going to be inclusive. Positive 2 is going to be it does not exist, and then 3 is another 0, and that is going to be inclusive. So quickly doing our sign chart, we might test like -10. So our test values are up here. We're testing -10. Make sure you show your work on that. So when I test -10, I end up with a negative times a positive over a negative. So I end up with a positive value, and we are happy with that region. That one's going to work for us. That's going to be true. Between -2 and 2, I think it's easiest to test 0. And when we test 0, we get a negative times a positive. In fact, x plus 2 squared is always going to be positive. All over x minus 2 or -2, that is going to be a negative. So that also is going to be a positive region. We like that guy as well. That one is true. From 2 to 3, we might test something like 5/2, and we get a negative times a positive over a positive, which is a negative value. So we don't like that. That one's false. We won't use that region. And we test something like 5, and we get a positive times a positive all over a positive, which is positive. So we like that region, and then we'll go ahead and put in our interval notation. So where our function is greater than or equal to 0 goes from -infinity. We go past this -2, and that's inclusive, so we can cruise right over that all the way to +2, non-inclusive, and then from 3 to +infinity. In example 5, it says the graph of the rational function is at the right. We're just going to use the graph to solve the following inequalities. So h of x is less than or equal to 0, so we want y is less than or equal to 0, or negative values, and our y's are negative. We have an asymptote here at -3. It looks like from -3 to -1, and then again from 2 to 3. So we write our interval notation. The asymptotes will be non-inclusive, but the zeros are going to be inclusive. In B, they want the y values that are greater than equal to 2, so we have a horizontal asymptote here at 2. So the x's, in which the y's are greater than 2, go from -infinity to our asymptote at -3. And it also goes from our asymptote at 3 to +infinity. So in interval notation, we'll write that as -infinity to -3, non-inclusive, and union with 3 to infinity. And then finally, h of x or y is greater than 0. Well, we're going to include the answer from B and C because 2 is greater than 0, so we got to include those guys. But there's also other positive y values here between 1 and, or pardon me, between -1 and 2. So those y's are positive in there. So we'll include that in our interval notation. So the final answer there, -infinity to -3, in union with 3 to infinity, and then between -1 and 2. Now those are non-inclusive because we have non-inclusive in our inequality here. So we don't want it equal to 0, we want it greater than 0. So that's why the -1 and 2 are non-inclusive. So there are some examples of graphing rational inequalities, and you'll get some more practice with this when I see you in class.